So we're given the water being pumped into the tank at a rate modeled by W of T, which they give us 2,000 e to the negative T squared over 20 liters per hour. And then it also says that we got water being removed from the tank. And this chart gives us R of T, which is the rate at which the water is being removed. And we know that R of T is, or we know that R is differentiable, and we know that R is decreasing. And so we know that the amount being pumped out of the tank is, or the rate at which it's being pumped out of the tank is decreasing as we go forward in time. And we know that at the beginning there's 50,000 liters. That's an important thing to note the initial condition. It's 50,000 liters of water in the tank to start with. So first thing it wants us to do is estimate R prime of 2. Well, to estimate the derivative of R without having a function that represents R, best way to do that is an average rate of change or a slope. So we can say that R prime of 2 is approximately equal to the average rate of change between 1 and 3. So that'd be the change in the function's value. So 1190 minus 950 over the change in time, 1 minus 3. Just a slope, right? y2 minus y1 over x2 minus x1. I guess I did 1s minus 2s, but same thing, doesn't matter. And that ought to give us, let's see, what is that? 50, that's 240 over negative 2, so negative 120 indicate units of measure. So the derivative of liters per hour ought to be liters per hour, or liters per hour squared. Any questions there? You got 1 point for negative 120 and 1 point for the correct units, liters per hour squared. Okay, everyone's good there? Perfect. All right, part B says use a left Riemann sum with 4 subintervals. So they're just talking about a left rectangular approximation to estimate the amount of water removed from the tank during the 8 hours. So effectively what we're doing is we are trying to find the integral from 0 to 8 of R of T dt, right? Because if we integrate the rate at which it's removed, that should give us the amount that is removed. So the integral from 0 to 8 of R of T. And says use a left rectangular approximation or a left Riemann sum with 4 equal subintervals. So that'd be, actually it doesn't say 4 equal, just 4 subintervals, which is what we've got here. We got 0 to 1, 1 to 3, 3 to 6, and 6 to 8. They don't have to be equal. If they're not equal, you just have to pay attention to the width of each subinterval. So the first one should be a height of 1,340 times a width of 1 from 0 to 1. The next one should be a height of 1,190 times a width of 2, or 3 minus 1. And then the next one should be 950 times a width of 3 from 6 to 3, and a width, or 740 times a width of 2 from 6 to 8. And what does that come out to be? Let's see. Should be, I think, 8,050. Does that sound right? Cool. I'm going to say that sounds right. Yeah, that looks, yeah, that's what the answer key says. So perfect. Okay. Then we want to know if the value that we got there is an overestimate or if it's an underestimate of the actual amount of water that is removed. And so we have a function, it says, that is decreasing, always decreasing on the interval from 0 to 8. So if you have a function that is always decreasing, the integral using a left Riemann approximation should always extend above the decreasing function. So it should be an overestimate because R is decreasing. Everybody good there with part B? 3 points for part B, 1 for the for setting up this sum, 1 for correctly evaluating it, and 1 for overestimate because it's decreasing, because R is decreasing. Everybody good there? All right, part C says use our answer from part B, so our 8,050, to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Well, the total amount ought to be however much we started with. Should be initial plus how much enters minus the amount removed. So our initial amount was 50,000. The amount that enters is the integral of this from 0 to 8, because we're talking about that interval. What was it, W of t, I think? I'm not going to write out the whole function, but yeah, W of t. And then the amount that is removed is 8,050. And we'll just use a calculator to evaluate that integral. And looks like to the nearest liter that came out to be 49,786. And that one was worth 2 points, 1 for using this integral and 1 for the final answer. Good or no? Any questions or issues with that? All right. And then part D says for 0 to 8, we want to know, is there a time t when the rate at which the water being pumped into the tank is the same as the rate at which the water is being removed from the tank? And so in order to figure out if those rates are ever the same, what we need to do is look and see if the value going into the tank is ever equal to the value leaving the tank, which would effectively be the same as looking at is W of t minus R of t ever equal to 0. Right? And so since we know that both W and R are continuous functions, right? W and R are both continuous, and that means that W minus R is continuous. And then if we were to use the intermediate value theorem, if we could find a time when W minus R is positive and a time where W minus R is negative, then we should be able to say by the intermediate value theorem, since it's a continuous function, there must be a place where W minus R was 0. And so if we were to look back here, if we were to plug in W of 0, let's say, W of 0 should give us 2,000. And R of 0 is 1340. So we could say W of 0 minus R of 0 is positive, but W of, if we went in and used the value at 8, let's say, W of 8, so if we plug in 8 to this, we could figure out what that value is. But that's 2,000 over e to the, what is that, 64 over 20, which is 32 over 10 to 3.2. That's going to be a fairly small value. Anybody have that value? For W of 8? Nobody? Okay, I guess I'll have to figure it out. $81.524. Okay, great. So that's 81.524 minus R of 8, which is 700, which is less than 0. So W of 0 minus R of 0 went from positive to being negative. So that means that it must have crossed through 0. And if W minus R was equal to 0, then W must have equaled R at that point. So by intermediate value theorem, yes. And the point breakdown for that one was 2 points. One for looking at W of t minus R of t, and one for saying yes by the IVT, and some, having some proof of that over here. Any questions there on part D?
So you had to use intermediate value theorem. There's like no other way you could have done it.
I mean, you could. I don't see any other way to do it since you don't have a function for R offhand. I mean, I don't know. Did you try something else? Maybe I'm just not seeing something else that seems obvious, but.
I didn't really do it right. I just like graphed a W of t and then looked at the values of R of t and then like saw that they crossed over and said that they intersected, which wasn't a solid proof.
Yeah, you would get probably no points for that. Yeah, you got to use one of the theorems. Usually when they're like, is there a time when this happens? Usually it's one of those theorems, intermediate value theorem, mean value theorem, one of those theorems. So. All right. Are we ready to look at this one?
Yeah.
All right. So we got rainwater flowing through a drain pipe. Got a function R of t is 20 sine t squared over 35. That's the rate at which it flows into it. Pipe is partially blocked, so water drains out, but not, one would think, not as fast as being pumped in normally. Drains out at this rate, and it has 30 cubic feet of water in the pipe at t equals 0. We want to know how many cubic feet flow into the pipe during that 8-hour time frame. So all you got to do for that is just integrate from 0 to 8 R of t dt. And integrate the rate at which it flows in on the time period. And that gives you 76.570. 2 points, one for the integral, one for the answer. Hopefully part A should have been a nice, easy 2 points.
Yeah.
Okay. Part B says, is the amount of water in the pipe increasing or decreasing? Well, the amount of water in the pipe is the integral of R minus the integral of D. And so if you took the derivative of that to find out if it's increasing or decreasing, that'd be, is R minus D greater than, or is it less than, greater than or less than 0? That'll tell us if it's increasing or decreasing. We're specifically talking at 3. So we've got R of 3 minus D of 3. You've got a calculator to evaluate both of those. And R of 3 minus D of 3 came out to be negative 0.313 something something something. 632 it looks like, which is less than 0. And since that's negative, it must be decreasing. Any questions on that?
Nope.
All right, let's take a look at, not this, part C. Where did it go? There we go, part C.
What
We
was
want to
the
know
point
at what
breakdown
time.
for B?
Oh, yeah, sorry. 2 points. 1, if you looked at R of 3 and D of 3. 1 for decreasing with a reason. All right, so now we are looking at what time is the amount of water in the pipe at a minimum. So we need an equation to represent the amount of water in the pipe. Well, the amount of water in the pipe ought to be the initial amount of water in the pipe plus the amount of water that's put into the pipe. So that'd be 0 to t at any value t of R of x. And then minus the amount that drains out, so 0 to t of x dx. We want to know specifically when is this amount at a minimum. So to find when the amount is at a minimum, we'll just call this W, amount of water. So we'll take the derivative of this. The derivative W prime is just R of t minus D of t. So if we want to know when it's at a minimum, we have to set that equal to 0. Setting it equal to 0 using your graphing calculator to just figure out where those intersect tells you that R of t equals D of t at t equals 0, and also at t equals 3.271658. And then because this is a closed interval that's given to you, 0 to 8 inclusive, you also have to check at 8. So you just make a little chart here. Here's 0, here's 3.271658. Here's 8. So these are our t values. And what are our values of W? So we'll just plug it back in to this equation to find each of those values. We get 30 there. When we plug in the 3.2 something or another, we get 27.964561. And when we plug in 8, we get 48.5436 something 86 it looks like. So it looks like the minimum amount is at t equals 3.272 hours. And that was 3 points for that one. 1 for figuring out it when R of t minus D of t equals 0. 1 for the answer, and 1 for a chart showing your justification. Any questions there on part C?
For some reason, for my answer, I got like 3.228. Would that not get me the point? I don't know why I got that.
That would not get you the point.
Okay.
Yeah, I mean, sometimes they give you like a little leeway, but like their little leeway is like 1/1000th one way or the other, not 5/100ths. So I don't know, maybe your calculator is not in radians. That'd be something to check since there's a sign in one of those functions. But if your other answers weren't off by anything, then that's probably not the issue. You might have just typed something wrong.
Yeah, probably did that.
Yeah. All right. Part D. The pipe can hold 50 cubic feet of water before overflowing. For T greater than 8, water continues to flow into and out of the pipe at the given rates until it overflows. We want to know if we can write an equation involving one or more integrals that gives the time when the pipe will overflow. Well, we had an equation for the amount of water in the pipe. So we just need the amount of water in the pipe to equal 50. So all we've got to do for part D is say that 30 plus our integral from 0 to, well, they want to know the time W, so we'll call it W of R of t dt minus the integral from 0 to W of d of t dt equals 50. Or you could put those together as one integral if you wanted to, it doesn't really matter. And 1 point for having the right integrals and 1 point for the full equation of the 30 plus and the equals 50. Everybody good there?
Yeah.
All right. Let's do the last. This is the last one I think that I had you guys do, right?
Yep.
Okay. I got unprocessed gravel arriving at a gravel processing plant. This is the rate at which that happens. And then the beginning of the day, it has 500, so we have an initial amount. And the plant also processes the gravel at 100 tons per hour. So we want to find G prime of 5. Well, G prime of 5 should be easy enough since you're given G and a calculator. Just evaluate the derivative of that on your calculator. So G prime of 5 came out to be negative 24.588. And then it says using correct units, interpret your answer. So the derivative of G, so G is given to us in tons per hour. And if T is measured in hours, then this is tons per hour, or tons per hour squared. So let's say tons per hour or per hour squared, whichever you want to write. And so it tells us that since this is the derivative of the rate and the derivative of the rate was negative, it tells us that the rate at which the gravel arrives is decreasing. Okay. So you can't say that the amount of gravel is decreasing. It's the rate at which the gravel arrives is decreasing because this is the derivative of the rate function. Okay, its derivative was negative. Good or no? And you'd write a full thing out, like saying the rate at which the gravel arrives is decreasing at 24.588 tons per hour when T is 5. 1 point for the right answer there and 1 point for the explanation with your right units. So 1 point for negative 24.588. The units is part of, you got to use your units in your explanation down here. Any questions there on part A? All right, part B wants us to find the total amount of unprocessed gravel that arrives during the hours of operation, which is apparently 0 to 8. So that'll just be the integral from 0 to 8 of G of d dt. And that should be 825.5 0.51 tons. And they gave you 1 point for the integral setup and 1 point for the answer for that one. Nice, easy points for part B. Good or no? Okay, part C wants us to find out if the amount of unprocessed gravel at the plant is increasing or decreasing at t equals 5. Well, that would depend then on if the rate at which it is arriving is greater than or less than the rate at which it is being processed. So we want to know if g of 5 is greater than or less than 100. So we'll say g of 5. You just plug it into the equation there to find out what g of 5 is. Comes out to be 98 point something or another. 98.140764. And since that's less than 100, the rate at which it's arriving is less than the rate at which it's being processed, which should tell you that the amount is decreasing. Less arrives than is being processed. We're having less at that time. Show the work. So there's not a lot of work there, but basically just saying finding g of 5 and then showing that it's less than 100. Part D, any questions on that? 2 points on that, 1 for the value of g of 5 and 1 for comparing it to the 100 and showing that it's decreasing.
If you didn't do it like exactly that way, would you still get the points? Like I did a sine graph of g of t minus r of t, and I like showed it out and saw that at like t equals 5, it's negative. Would I still get the points there? Or do I have to do it the specific way?
You did a sine chart of g of 5.
No, just of g of t minus r of t.
Of just of g of t, sorry, yeah, g of t minus, basically g of t minus 100.
Oh yeah, I labeled that as r of t, my bad.
Yeah, okay. If you said g of t minus r of t or g of t minus 100, and you saw that that value was negative there, yeah, then that's fine. Yeah, if you, as long as you define the g of 5, or sorry, the g of t minus 100 equals the rate of change of the gravel or something like that, then that'd be fine.
Okay.
All right, part D, we want to know the maximum amount of unprocessed gravel. This is very similar to the last one we were just looking at. So we need to write an equation to represent the amount of gravel, right? And the total amount should be equal to the initial amount, which I believe was 500, plus the amount that was brought in from 0 to t, which we call g of x, and then minus the amount that goes away, 100 dx, the integral from 0 to t of 100 dx. You could have put the 100 together in that same integral, or you could have just said minus 100t after that integral. That would have worked as well. But anyway, all you needed to do then was to figure out when this amount is at a minimum. It was asking for a minimum, I think. Or was it asking for a maximum? No, maximum. Figure out when a prime equals 0. So that'd be when does g of t minus 100 equals 0, or when does g of t equal 100? And that happened at, looks like t equals 4.92348. And we make a little chart here, values of t and values of a, our final amount at 0 at 4.923, And at the endpoint of 8, plugging in 0, you know, gives you 500. Plugging in the 4.9 whatever gives you 635.376. And plugging in the 8 gives you 525.551. And so we would see that the maximum amount was 635.376, and that occurred at 4.923. So 1 point for looking at G prime minus 100 is 0. 1 point for your answer here, and 1 point for the whole chart showing the justification. Good or no? Any questions or issues there? All right, I got a bunch more for us to take a look at, and I'm going to post the ones we don't get through today. I think we'll probably only have time for just the one in class today, but then I'll post the rest you can work on this evening if you'd like, and I can answer questions through Remind. Anybody have any questions on any of the ones we've done so far? All right. Let's take a look at, I guess we could do this one. It's a little bit different. I don't know if I like this one. I don't like yeah, let's just do this one. All right, we're gonna do this one. A cylindrical can of radius, whatever, Stormville and Monsoon Mountain. Very exciting names in this one. All right, so I give you guys 15 minutes to work through this, then we'll go through it, and then that will be probably it for today. So
is this one up in the driver now?
No. I'll get it up.
That's
there.
fine.
All right, I won't get it up there then. All right.
Yeah,
I'll have it up this afternoon, so you can have a record of it later. But yeah, I'll just leave it for now because I gotta adjust this and put some more into it before I post it later, I think. All right, 15 minutes to work through this one. Ready, go. So part A, according to the model, we want to know the height of the water in the can that's in Stormville at the end of a 60-day period. So they give us the rate at which the water is increasing, and we know that it starts at 0. So all we need to do is figure out what the integral from 0 to 60 is of s prime of t dt, right? S prime being the rate. And looks like that came out to be 171.813 millimeters. And they had 1 point for the right limits there, 1 point for having s prime, and 1 point for the 171.813. So 3 points for that first part. Pretty straightforward, I think. Everybody good with part A?
Yeah.
Cool. Part B, we want to know what the average rate of change in the height of the water in the can over the 60-day period is. So if we're looking for the average rate of change, that's just a slope. And so the slope ought to be the value of the height at 60, which would be 171.813, minus the height at 0 over 60 minus 0. And that comes out to be 2.863. And it says include units of measure. And so this is, we've divided by 60 for 60 days. So this should be millimeters per day. That's the average amount that the height is increasing.
I use the mean value theorem for integrals on this one, but I still get the point for that. I got the same answer.
Yep, that's totally fine. I mean, this is effectively the mean value theorem using this function. Because this is S of 60, this is S of 0. 60 minus 0 is your 1 over B minus A. Same thing. But 1 point for part B. All right. Part C is a little different than the ones we've seen, I think. So it's assuming no evaporation, so we're pretending we don't live in the real world. We want to know at what rate is the volume of water in the can changing. So we need a formula to represent the volume of this can now rather than just the height of it. And so what's the volume of a cylinder? It should be pi r squared times the height, right? And the height is our function S of t. So for part C, we're looking at pi times the radius squared times S of t is the volume, or 100 pi S of t. And so we want to know at what rate is that volume changing at t equals 7. So that would be volume, its derivative at 7, which ought to be 100 pi S prime of 7. And that came out to be 602.218. And it says again to indicate units of measure. So volume, if it was millimeters, should be millimeters cubed. If it's a rate of change where t is in days, it'd be millimeters cubed per day. Any questions there on part C? All right. And part D. We've moved on from Stormville. Well, not moved on, but we're still dealing with Stormville, I guess. And we're also now looking at Monsoon Mountain. So same 60-day period. We got rain accumulating in an identical can. The height of that one is this function, also millimeters, also days. And they're giving us this function, capital D of t, which is m prime minus s prime. And we'll note that they're giving us m rather than giving us m prime here. M is the height. Up here, we're given s prime, which was the rate. But for this one, we're given the actual height function. So then it says we want to apply the intermediate value theorem to the function d on the interval 0 to 60 to see if there exists a time where the heights are changing at the same rate. So first off, we'd want to think about the function d. Right? Function d is a continuous function because we know that the integral of this is continuous, and we know that the derivative of, or actually, we don't need to worry about the integral of this. We know that this function is continuous, and we know that this function's derivative is also continuous. It's just a polynomial. So we can say that since d is continuous, that's the first, the first criteria for the intermediate value theorem. D is continuous on our interval 0 to 60. And so then what we want to find out is if d changes values anywhere between 0 and 60, or if it goes from positive to negative. And so good places to check would be starting at d of 0 and where it ends at d of 60. And so d of 0 we should be able to find because we can just plug in the derivative of this at 0 and then subtract this at 0. Right, so d of 0 is m prime of 0 minus s prime of 0, just from your calculator. That comes out to be negative 0.675. And d of 60, which would be m prime of 60, which you can use your calculator for, and s prime of 60, which you can also use your calculator for, comes out to be a positive 69.9 9.3773 something. And so because there is a sign change on D from negative to positive, there is a place, and we probably note that this is less than 0, greater than 0. So by the IVT, D of t equals 0, somewhere on the interval 0 to 60. And if D of t equals 0, that means that M prime of t equals S prime of t, somewhere on that interval. And those are the rates, which tells us that the rates must be equal somewhere on that interval, which is what I was asking. Good or no? That one was worth 2 points, one for looking at D of z equaling, D of 0 and D of 60, and 1 for this explanation with the intermediate value theorem. And then that leaves 1 extra point from all the other ones, and it says that at the end, if you had the right units in either B or in C, you got 1 point for that. Any questions there on that one?
What was the point breakdown for C?
For C, I didn't tell you guys that. For C, it was $1 point for writing an equation for the volume and 1 point for the answer. And then, like I was saying, it was 1 point for having either the right units here or the right units here. And
So there was like an extra point, not
I mean, it was
attached
still
to
a
the
total of
question.
9. So you had 1, 2, 3,
Okay.
4, 5 here, 6, 7. Oh wait, no, we had 1, 2, 3 up here, 4, 5, 6, 7, 8, 1 for those units that we're talking about.
So did you need both, you said, or just one?
It says units in B or C. So if you had the
Okay.
units in one or the other of them, then you were good. Any other questions there on that one? How do we feel about these rate questions overall? Are all good with them?
Yeah.
All right, that is going to be it for today.